All right, guys, go ahead and copy this diagram. Here you have a ramp. The ramp has some angle of incline labeled theta, and you have an object. This object has mass. It's a box in this case, and I've labeled the object's center of mass with a dot. Newton's first law states that all objects with mass resist a change in their velocity. So it doesn't matter an object traveling at a constant 100 miles per hour or an object that's totally at rest. From the perspective of Newton's first law of motion, those objects have no net force acting on them. So an object moving at 0 meters per second or 100 meters per second, it's the same. There's no net force acting on those objects. In this case, our object is going to have a net force. So to analyze objects like this orange box on an incline, you start by drawing the most obvious force, which is the force of gravity. The force of gravity is typically drawn from the center of the object's massive distribution down towards the center of the Earth. This is the weight of the object. The force of gravity equals mass times little g. Little g is the gravitational acceleration. What prevents this object from accelerating through the ramp is the normal force. The normal force is normal to the plane of any surface, that is perpendicular. It is at a 90-degree angle from the plane of the surface. It is a reactionary force in accordance with Newton's third law. For every action, there's an equal and opposite reaction. So whatever component of the object's weight that happens to go perpendicular to this ramp, the ramp opposes that weight. The ramp supports the object's weight and prevents the object from accelerating. Because this object is at an angle on the ramp, in order to define or to calculate this red vector, this red arrow, I have to analyze a little vector triangle. So I will extend this arrow, this red arrow, down through the surface of the ramp. And I will note that the angle between the normal force, the red vector, and the force of gravity, the black vector, is the same as the angle of incline. Don't forget this, write this down, make this just part of your memory. This allows me then to analyze a vector triangle where the weight is the hypotenuse and the adjacent side with respect to the angle is the normal vector. So the normal force is calculated by multiplying the hypotenuse, in this case the weight mg, by cosine theta. All right, now this object is going to be accelerating down the ramp. Why does it accelerate down the ramp? Because a component of gravity sends it down the ramp. I'm going to label this component in purple. It is parallel to the surface of the ramp. It is parallel to the surface of the ramp, parallel to the surface of the ramp. Don't draw anything crazy. A lot of people, sometimes I've seen people try to draw it like this, having this. No, it is parallel to the surface of the ramp. It's what guides this object down the ramp's surface, so it must be parallel to the surface of the ramp. And I'm going to translate this vector up here out from the center of mass to show that this is what's going to guide this object down the ramp. So just like before, I can define what this vector is. I can calculate this vector by analyzing my vector triangle where the weight is the hypotenuse. When I do that, I like to label it force down the ramp. This is what guides the object down the ramp, equals mg, the weight, sine theta. Okay, for your simulation, this is also going to have friction acting on it. So let's go ahead and draw this force of friction vector. Again, this is parallel to the surface of the ramp. Friction is a contact force. To calculate the force of friction, either kinetic or dynamic where the object is moving, or static friction where the object is stationary, it's pretty much the same formula. You have this mu symbol, mu, like the Pokemon. Mu is the Greek letter mu. It's a U with a tail in the front times R, where R is the normal force. If I replace r with its equation mg cosine theta, I get mu times mg times cosine theta equals the force of friction. So we've covered a little bit. Newton's first law of motion states that all objects have mass or inertia and they resist a change in their velocity. Newton's third law, for every action there's an equal and opposite reaction. In this case, the object exerts weight on the ramp and the ramp exerts a force back on the object equal to a component of the object's weight. If this were flat, it would be totally equal. The normal force would be totally equal to the object's weight, but we're at an angle. So Newton's second law of motion states that if you have a net force, F net, it causes the object to accelerate. Net force, F net, equals m times a. What is the net force acting on this object? In this case, the object moves parallel to the ramp. It doesn't accelerate up and down through the plane of the ramp or the surface of the ramp. It accelerates along the surface of the ramp, doesn't go up and down through the ramp, along the surface of the ramp. So I look at these two forces acting on the object parallel to the surface of the ramp. I keep stressing this for a reason. So my net force is the vector addition of these two forces. I choose down the ramp, the direction the object is going, to be the positive direction. This is the positive direction. Remember, force is a vector. And then I'm going to add it. I'm going to add this force down to this vector, this force of friction vector, but this is going up the ramp opposite to where the object will accelerate. So this will be the negative direction. You should choose positive and negative when it comes to forces. Choose the direction the object is actually traveling in. Choose that to be the positive direction, even if it ends up being down. For kinematics, it makes more sense. It's simpler to go with the coordinate system. But for forces, the direction the object travels in becomes the positive direction. The net force is a combination of these two. F net of this object equals the force down. In this case, it'll be minus the force of friction. You subtract because the force of friction vector points in the opposite direction of the force down vector. And then it just becomes a simple matter of replacing F net with mass times acceleration, m times a, equals force down, mg sine theta, minus force of friction, minus mu mg cosine theta. And if you do this correctly, you'll see, hey, mass doesn't even matter. Copy this, have your net force equations copied into your one notebook, and this is how you'll get your grade for this flipped assignment. Thanks for watching.